Okay, great. So, whoops.
Close that window.
Die.
Okay, last speaker of this section is Patrick Sanan from ETH Zurich. And he's going to talk about staggered grids.
Okay, thank you. So this will be the last talk and perhaps a slightly different one. I'm going to be proposing a new component for PETSc, which, as it says here, is a staggered grid implementation of DM. So I'll try and do a quick one-slide application as to what our motivating application is, even though I hope it'll be more of a generally useful topic. There's sort of a class of simulation codes for doing mantle and lithospheric dynamics that are used to simulate things from regional dynamics to multi-billion year evolution of the entire mantle and lithospheric planet. But the unifying thread between all these codes is they're all based on quite a simple discretization. They're solving something that looks like a Stokes system, so some momentum conservation, some incompressibility or mass conservation, coupled to some energy equation, usually done with tracers, particle and cell methods. And they use a particularly simple discretization, which is a staggered grid. So of course the logical question then is, can we optimize that grid? So a little more motivation as to why you want to even think about optimizing a finite difference grid, a sort of orthogonal finite volume method, if you like. These are simple. They have very narrow stencils, so the operators are very cheap to apply. This is quite useful in the application domain here, where we have very sort of arbitrarily varying and widely varying material coefficients, sort of across arbitrary interfaces in the domain. So in many of the applications, we are reduced to first-order accuracy no matter what we do. So for this reason, we argue that in this corner of the domain, it can be actually quite efficient to use these simple discretizations. And they've been very scientifically productive. A lot of the research in long-term geodynamics has used these application codes. So despite the fact that they've been very successful, there are still some bottlenecks in these applications, which we hope to address. We have non-uniform performance amongst codes. They're mostly hand-rolled. Not everything can be arbitrarily parallelized. It's not as easy as putting in the number of MPI ranks you'd like to run on. Critically for PETSc, they can't all leverage the vast array of solvers that are accessible. And they can't really share optimized operations, even the ones that already use PETSc, because they have different ways of using PETSc, in particular DMDA. So we have a project funded by PASC, the Swiss Platform for Advanced Scientific Computing, to develop a sort of lightweight backend for all these codes to optimize them. So there are some sort of known scientific objectives that can be achieved just by increasing the resolution of known codes. So that's the first application for an optimized staggered grid object. In the future, we'd like to introduce analysis tools and more advanced solvers once we have a common framework. So this is the project. I'll be talking about the first component of it, which is a DMStag object, which we'll couple to our own grid object in the library. So this is my working definition of what a DM is, which informs the development. I think of it as these four things, which are sort of a fancy word and then perhaps a less fancy word here. Some topology, so what points are connected to what points. An atlas, which points go to which subdomain, so what the charts are if you want. What the embedding is, what coordinates we put on top of this mesh, and the section, so what data lives on the mesh. So perhaps the critical...
I know this is like going to start fights, but is it obvious that the embedding is part of the DM?
It's in the data structure for the DM. It's not essential that you have it there. So there's another DM in there, which is the coordinate DM, which is usually a compatible DM, as I'll discuss later. This is my view. I'm not sure if this is canonical, so I would like to get...
It can be a field with a section just like any other field now.
Okay. Well, I'll ask you afterwards whether it's intended to have more than one section per DM or not. But at least for my purposes, I'll be treating sort of two fields living on the same domain as being two different DMs because the sections differ. So in developing this, I've introduced an idea of compatibility. So if you want to argue more about this, there's an issue on Bitbucket, which is still open. Sorry, I tried to fix this just now, but I propose to implement or to add something to the API, which will tell you if two DMs are compatible, which means essentially can I iterate over them together, do sections on one are they interpretable on the other one? So we already do this all the time when we have multiple DMs that represent the same domain with different fields. For DMPlex, this is very easy because these first two things are really encapsulated in exactly the data pointer, so you can compare that pointer and get positive confirmation of compatibility quickly. What's missing here is that I have actually two output arguments for this function, one of which is, are these things compatible, and the other one is, did I return an answer or not? You can imagine comparing two compatible DMPlexes with different data pointers would be perhaps time-consuming, so I wanted to leave some freedom in there to refuse to answer the question. So here are some design drivers for DMStag. I'd like to look as much like DMDA as possible to make it easy for users to adapt to, and also to reuse the technology there. As with DMDA, I'd like to emphasize not having the user understand anything about local ordering or even PETSc ordering if possible. Try and keep it simple. Of course, allow for efficient operation for the target applications for this project, but hopefully for other ones. When in doubt, optimize for 3D, and allow for some extensibility for other components of PETSc as listed here. So particle methods, hopefully use it as a base DM for DM Forest at some point. And perhaps introduce some of the more advanced section handling things that are in place for DMPlex. And I think even for DMDA, that's not documented. So here's the numbering scheme for DMStag that I propose. So this is supposed to be what the user reasons about. This is a sort of global natural ordering, and the user is only supposed to really understand the numbering of the elements. So this is the 2D example. The ordering is sort of x fast, y second fast, as in PETSc ordering. Things that are perhaps non-obvious are that you can refer to an item outside of the domain if you'd like to. So if I'd like to refer to this edge, I could refer to it with respect to this element. And also there are non-unique names for points. So this point here between this element and this element, I could refer to it by this element numbering, so 3, 1, and then say it's the up face, or I could say it's 3, 2 in the down face. And indeed this one I could say is 4, 0 left face if I'd like to. So this gives the user sort of some flexibility of how to think about placing things on the domain. And then of course each one of these points has a certain number of degrees of freedom associated with it. So we define the usual sort of global to local map. The coloring here corresponds to which rank, in this case 4 ranks, you'll send things to. A key point with the local representation is that I add in these sort of dummy points so that we have a constant number of entries in the local vectors per element. So in this case, every element is associated with 4 entries. So we have this block of 4 things. So for our local operations, we have a regularly blocked data structure, which I think will be important for performance later. These are the numbering schemes that are used internally, so there shouldn't be any surprises here. This looks a lot like PETSc natural ordering for DMDA. So we number things from the bottom left going in Z's up. The global PETSc ordering is this ordering per rank. The local ordering, again, is in blocks of 4 here. So we can see we have exactly 48 points on the local domain. And then I've somewhat arbitrarily chosen to number the points within each element in the same way, so sort of bottom left, top right. So we number sort of vertex, edge, face. So the API is supposed to look a lot like DMDA, so this is how you create a DMStag. The differences are that you can now describe several degrees of freedom that live on the different strata. Otherwise, it looks almost exactly the same, I would say. This is just a quick view of the current data that I'm storing in the DMStag object. I'm going to try and show you quite a bit of code to see if I get any feedback on the syntax being ugly, perhaps. But we have things that you set before setting up, things that are populated with DM setup, extra stuff as well. I think the only thing here that's not order 1 is this, which is perhaps not essential. So this should be a pretty lightweight object. And that is, of course, order B, I think. So to try and make it easier to assemble operators and indeed vectors with DMStag, I propose a object that looks like mat stencil, but is called DMStag stencil, and differs only by the addition of an extra integer, essentially, which tells you which one of these sort of subpoints in the element I'm referring to. And then the API can accept vectors of these stencil objects and use them to populate vectors and matrices. So here's a big block of code. Hopefully most of this looks familiar if you've used DMDA, but there's a few things that are different. So instead of creating a compatible, the example here is something you would do pretty frequently in just doing output, is I want to take a mesh that has sort of things living on the boundaries of my cells, and I want to interpolate them to a multi-dimensional thing living in the center of my cell so I can dump it out to ParaView or something else that doesn't really understand staggered grids. So the operation here is just an averaging that I'm doing between the boundaries of the cell and the center of the cell. I'm using these stencil objects here, much in the way I'd use match stencil to specify locations. The rest of it, I think, is fairly standard-looking PETSc boilerplate. It's kind of convenient to write this way if I'm assembling both a matrix and a vector, and then I can use the stencil objects. It might not be the most efficient, though, so just like with DMDA, I also propose a direct array access to DMStag vector data. So I implement DMStag vecGetArray DOF, which is similar to DMDA vecGetArray DOF. Perhaps that name is a bit confusing, but it operates in much the same way. And then it gives me a raw pointer to a multi-dimensional array, which I can use to access my points. And of course, this works in a low overhead way because I've defined the local points to have a sort of integral number of elements worth of data in the local representation. The trick is to call this sort of function here to figure out what slot in the local domain I actually mean for each particular degree of freedom. So if I want to talk about something on the left face of an element, I can put in DMStag left there. I can get out an integer, which gives me something which I can use over and over again in my loop. And this is not restricted to any particular direction. I can just as well put DMStag up there, and it'll give you the correct offset. So I can still get things out of this array efficiently. Okay, so another common optimization that I thought would be useful to include in the API itself is a notion of product coordinates. So all the applications I showed at the beginning use orthogonal meshes, and they use finite difference stencils which are only going to work on orthogonal grids. So storing all the coordinates is perhaps redundant, so I propose a very lightweight DMProduct implementation, which does little more than hold the local Cartesian product of DMs. And you can use this to access your coordinates in the same way that you would for the entire mesh, but of course with an over p squared reduction in the amount of data you're storing. So here's some more blocks of code. This is just assembling pretty much the simplest stencil, which is a continuity equation with a regularly spaced grid. It looks a lot like using that stencil. You populate these little structs, you tell it which element you'd like, which direction on this element. I've omitted prepending these intermediate values with DMStag just by redefining them in the examples. And here I'm using the stencil-based methods for putting things into a vector, but of course you might want to use the array-based one for efficiency. Here's the same thing, but using direct access to the arrays. Here's the same thing with direct access to the coordinate arrays. So they're indeed just a product of 1D DMStag objects in this case, so the access should be done in a similar way. This is still a bit ugly here, so I'm open to suggestions of how to resolve this, in that if I have a 1D vertical DMStag, I'm still using words like left instead of down in that case, which is a bit confusing. If you have multiple grids which you don't want to interlace as far as the data is concerned, you can use multiple DMStags. You can check them directly for compatibility to make sure you can iterate over them together. In this way, we're just pulling out some material properties, so densities and viscosities. So this is directly from an example in the textbook I was taking examples from. Here's what a momentum stencil looks like, the same sort of thing. And so with this, you can rebuild your simple examples. So I chose this one because it comes out of a very popular textbook that most of these application codes grow out of in some sense. So you can run the same example, get the same results, but now you can run an MPI on however many ranks you'd like. You can plug in custom preconditioners. You can do all your PETSc things with this, and hopefully it's not so much harder to write than it would be in MATLAB once you have PETSc already. Okay, so that was probably pretty fast. But in general, the point of this talk is to propose these three components and hopefully get some feedback on these components afterwards from talking to all of you. So I propose two new DM implementations, one of which is DMStag, which is a generalization, if you want, of DMDA, which has a nicely blocked local representation, which looks a lot like the local representation of a multi-degree of freedom DMDA. There's a lightweight DMProduct, which does Cartesian products of other DMs. You can imagine other uses for this product structure, perhaps, if you have a uniform vertical structure and a unstructured map over the globe, perhaps, or over an ice sheet. And I propose a new function for the DM API, which is to confirm compatibility, sort of simultaneous iterability for two DMs. So this is on the way to being finished. If you want to see my terrible in-progress code, it's here. But I'm hoping to get some input before I finalize this and make a pull request pretty soon. Okay, so I'll take any questions, and thank you.
Lawrence again.
So, this question is related to this last one. So when you showed the bin calculating velocity for the cell size, I do not understand at all why you need a new DM. So I think all of this compatibility nonsense is just a slide problem.
Sure.
What we want to solve is we want to represent multiple different fields on the same DM.
Yes.
The interface you have with DM is the DM can only have one section associated with it.
Right.
Which, frankly, I've never understood.
I mean, I would be perfectly happy with changing that.
Okay, you heard strict noise. I mean, my understanding of Bottlenecks is that, along the lines of the DM sort of representing at the highest level more of the function space on the mesh, and you can clone to keep the mesh structure on the back end so different fields represent on the same domain. Which makes a lot of sense from an unstructured point of view. It would be nice if this were kind of better represented on the structured world of tree. But I think that doesn't mean abandoning the outer interface of one main field per DM, but maybe you would want some way to say, okay, do these DMs have the same underlying topology?
So this is okay. So in my world, then what you're basically saying is that DMs correspond to function space.
Yes.
What's the thing that corresponds to mesh then?
That's the implementation. You could split it into, you could imagine splitting it into a topological interface and a function space interface. The problem is that you can't do it, but the split should be. And DM is a hard thing to split up because there's so much in there. You can make a whole bunch of useless objects trying to keep down the number of levels. So it's definitely one of these no choices but yet things that you're just not making it work. We originally had multiple fields for DM, and it's too confusing because then you end up making an extra argument for everything that says, look, I was really talking about this. And instead, it's much easier to just clone it every time you want it to represent a different thing. And the topology information is it stays in the background and gets shipped. And so that's why compatibility is pretty good, because it's pushing up to the interface level this stack that we have that actually
So in fact that get compatibility call is basically unearthing an implicit object.
That's right.
Mhm.
Yeah.
And I suppose in correct usage, you wouldn't need to call this as a user very much because you would try and make your DMs descend from one another. So I would create one DMDA, and then I would get a compatible one with the function, or it would clone a DMPlex or this kind of thing. So much like I should only.
Well, that's a kind of owning. That's an owning main kind of argument, right? As soon as you are, as soon as you're an a library on top of DMPlex, then who said that you're the one who made the DM?
Sure.
So,
But I suppose if I'm making a DM expecting it to be compatible with another DM that I have access to, then I should be cloning that one somehow. But I suppose if I can't, then I have this function as a user.
well, if I'm providing functionality that applies to two fields that had better be on the same mesh, then you need this because you don't control the construction of those two fields. Some of others did that.
Yeah.
So,
That's why we do.
yeah, no, that makes sense.
Yeah.
And I have another question about how easy would it be to find pieces of the stag that don't play by the rules. So the reason I say this is imagine that you do cubes here, because there exist people who want to do large stencils on cubes. And then when they get to these singular vertices, they just say, well, we'll do something else, and we want it to work like DMStag everywhere away from
I mean, you're free to write your own special cases for those points, I suppose. So, like for example, my plan for interfacing this with STAGYY, which has two grids overlapping, is simply to replicate their logic, which treats the boundaries differently. I think that this is probably below the level of that kind of thing. So you have to write a lot of stencils for a lot of these applications. So hopefully this sort of layer of upright, left, down stuff makes it a little less painful to write those stencils and debug them.
How generic do you imagine DMProduct is?
Well, for now, I just want it to support 3.1D DMs, which it does. But in general, I don't see why you shouldn't have a thing that is the complement of DM composite, which is a product of DMs as opposed to some sort of sum of them.
Maybe one final question for Richard.
Can you back up and show a picture of your staggered grid?
This one? Yeah, so this is supposed to be the user's eye view of this, which is, these are the numbers we expect you to talk about. If I go sort of get ghost corners, then I look at these, and then there's an additional output argument to get ghost corners, which is get the number of these dummy points, which is either 0 or 1, and that makes the iteration a little bit friendlier in some cases. Yeah. Yeah, so I'll usually have some option of like, if I want to talk about this point, I kind of have to do something special, so I can either iterate over all the points and then here say, am I on the boundary, now do something with the right one, or I can iterate over all the points and then talk about this one, but then only set the left boundary and not talk about sort of a pressure that's outside the domain. So there's some extra fiddling in all the examples for that.
Can you respond to all of the create sub and super DM codes?
No, I didn't address that at all.
That's the interface for breaking down the function space.
Yeah, so I have a function which is, get compatible DMStag, which does the same thing as get compatible DMDA, so it just returns the same thing. And then I have a function which is migrating a vector. So I'm not sure if that's actually useful in general, but
That's the analog. Maybe we could agree on that.
yeah, so the migrate function is in there. It's pretty simple. It just says if I have a vector which lives on a compatible DMStag, I can then migrate it to another one with a different number of points on each stratum,
Right.
and then just throw in zeros if it doesn't exist.
Okay,
And,
that's exactly what
yeah. So yeah, okay. I guess I re-implemented something that was already there.
Okay, so we need to move on to the next bit of the program. So let's thank Patrick again.
Yeah.
I'm just going to turn off the recording.